All right, okay. So we're going to talk more about this branching networks stuff that I made up, apparently. So now they exist. Other people exist. This Tokunaga guy existed. May still exist. I don't know. Hello, Lindsay. The New Jersey people look after each other.
Hey, you ready to go? It's like 2:18. I'm like, yeah. So I get my stuff and I was like, hey, you ready to go?
You want to go over the bridge?
No, he goes, oh, I'll see you there. I was like, what do you mean? He's like, well, I'm going to skateboard. You're going to beat me there? I'm sorry.
All right. We're good. I'm going to talk about branching networks. I wanted to find some nice little funny gag video of networks in football, but I didn't really come up with any. But there's the whole the plays thing, that kind of. But I did. So if you watch Colbert, he's had this thing about superb owls. So this whole week, because you're not really allowed to say the word I'm not going to say apparently, because you'll get fined by the NFL. So ads have the big game on them all the time. Please. But they're worried about it, So apparently it's true. Like Viacom is a huge company, but they're worried. Like, don't say it. So he made a whole joke out of it's about the superb owl, right? So there are owls. There's an owl theme. But here you go. This is from my journal. This is a while ago, right? This is 2010. I keep a lengthy journal. Of course, it's in LaTeX, right? But so there's some stuff here. Super Bowl is on. Blah blah blah. Doing some basic things. The superb owl. And I think I'm hilarious, right? It's going well. And then the Saints won. It's good. And then there's something about one of these branching network stories is going to be an economist. That's kind of nice. And then something about bicycles. But that's my diary. That's all you get to see of my journal. But I grepped because I'm like, I've said that. Colbert, you owe me. He doesn't owe me anything. All right, so anyway, it is quite funny. Okay, so we're going to talk a little more about branching networks. We're going to get into a little bit of math. Yep, so we're going to stand back a little bit. I want to remind you of the things we introduced on, was probably Tuesday, right? Trouble with the days of the week. I'm sort of getting a little, how is this doing? Do we need to turn the lights off? Sleepy time? Is that what's happened? Oh my. Okay. No? How about that? That's terrible. All right. Okay, so all right. So we had a couple. Let me get to a few of these pieces. So we had. Where's my thingamajig? Where's the little mouse thing? Okay. Wow, the mouse is unviewable. Why is that? There it is. Hello, mouse. Okay, so Horton's laws were about, so if we look at this, right, the stream ordering thing is the key here, right? So these are first order streams, these dash ones, we had this pairing idea, but really we think about when two first orders meet, you get a second order. First orders reaching any higher order, they get absorbed, and that's true in general. So these two second order ones, they're a bit thinner, they make a third order, and then these guys get absorbed in their side branching, right? So this was this picture we started to draw out of these things because we want to understand natural branching networks, which are everywhere. Okay, so Horton's laws, and these took 15, 20 years to figure out, but they're all usually attributed to Horton or Horton-Strahler. So it's the ratio of the number of different orders, adjacent orders as you go down, decreases roughly by a constant factor. Right, so it decreases, so this is a bit odd. There are less of those, of course, but they become longer and they drain a larger area on average. So these little bars are averages. So you're averaging across all the orders, all of the basins of order omega. So this is the longest stream in the thing, and this is the basin area. So these ones are wiggly, right? They can be, this is actually the stream. Yeah, wiggly streams. Right. So they grow, and they grow in a similar kind of way. So this is this fractal story, and it's been sitting around started in the 40s, very nice. Okay, so we had that one. For some reason, where's the little mouse thing? I'm just like stabbing at the. Nope. Okay. You're not going to tell me. I'm going to go to Tokunaga's law. So Tokunaga's law looks like this. So it's the number of streams going. So we're going to talk about stream segments, right? So this is a third order stream segment to here. When you're thinking about the mainstream length, it actually maybe goes all the way up here. Like you'd pick out this one as the longest stream in the whole thing, and it's a third order. But it's made up of a third order, a second order stream segment, and a first order stream segment. Okay? So we use this word segment. We'll have that a lot.
I don't know if it was the slide before, but what exactly, when it says T sub U, okay, there's the average number of sides?
Yeah, so there's streams that are being absorbed.
Yeah.
We'll use this word absorbed, right? So they're not changing the order. So you have two order 4s come together and make an order 5. And then 4s and 3s and 2s and 1s could come in. But they don't change this one until it hits another 5. Or gets absorbed into a 6 or a 7 or something like that.
Yeah, that makes sense.
Okay. Okay? I will seek to confuse you from here. So it has a self-similarity structure to it, so it only depends on the difference between the order, right? So, yeah. And then further, it has this kind of exponential growth structure as well, right? So there's when there are a difference of 1, then we just have T1 because this is mu minus 1. This will be a 1 minus 1. This is power of 0. And then it goes up by a ratio of this R sub T, Tokunaga ratio. Right? Typically, this might be 3 or 4. This is 2, usually, something like that. And so it grows up, it doubles. All right. So this is these are observed descriptions. They're very robust. I've showed you a couple of graphs from large continental scale things. A little bit from inside of us and other organisms that have been scrutinized through various methods. So very robust. It's out there. I want to connect. Today we'll connect them. We'll connect a few of these laws together, right? We'll start to reduce the description, which is very exciting. What's really going to be, as I've said, what really remains a great problem is trying to understand really the true provenance of all of this structure, right? Okay. So we'll get to that. I think that's what I want to just reprise from there. Okay, so we're going to get stuck into this stuff, and we're going to have to think a little bit. I will. You can just laugh at me. Okay? You will. Good. New Jersey. Okay, so no, it is your people. Okay, let's see. So these things seem quite different, actually, right? They seem to have different content. If you start to reflect on them, one is about the side branching structure. It seems quite detailed. Another is this sort of broader story as you go across. Doesn't seem to tell you about this side branching thing at all. So we'll kind of sneakily get out both of those pieces of information. So Horton seems to be, as I said, it's less detailed. It has this bigger overall sort of description. There are 4 parameters in Horton's description, right? We have one for area, one for number, and then these 2 length ones. There's the stream segments and the mainstream length. And we've already said that those last 2 are the same. All right. Tokunaga only has 2 parameters, so that's a bit odd, right? So if this is a micro description and it has 2 parameters and then it goes up to a bigger thing that has 4 parameters, you think maybe we've got some extra stuff floating around here that we need to clean up, right? Or maybe we're missing something with Tokunaga. It's a good problem. All right, so we have, here are our 4 ratios from Horton, and then these T1 and RT, that's all we need over here. So we've already had this. I've mentioned this, I think. Yeah. I really should bring chocolate. Keep people awake. Okay. Or it could be fun. Okay, so that's much harder. Just basic, go for the, injection of sugar and caffeine. Let's see. So we've already, you'll figure this out. This is not a huge thing, right? Little geometric sum piece, but you can see that they basically have to be the same thing. So that collapses. So now we've got 3. So that's an immediate thing. Sort of makes sense. They're both about lengths, but you can calculate that. Tokunaga's law is that gives you, as I said, this kind of more microscopic kind of feel. So if we see if we can build out from that and see if we can get Horton's laws. And this is what Tokunaga did actually. What I accidentally did as well, but this is certainly what Tokunaga did. So this is a known result. And then citations. Yeah. Okay. All right. So let's get that. we have to add one extra piece. So along the way, there probably had to be something like this. So there's one other piece in here. And you could debate how this might vary within organisms across landscapes, right? You think of deserts versus rainforests, and, especially if you're looking at continents. Okay. But it's space fillingness, right? So that's pretty important for us, right? We have to get the good stuff out to the cells, right? So we don't want to have cells too far away from capillaries. Which one? Okay. Capillaries. Okay, so thank you for reinforcing that. So basically, it means you have to think. We want to write down sort of an equation for this, but basically that the separation between, say we've got a stream and you've got some side branches here, that the typical separation here isn't too varied, right? It's not crazily different. We'll actually see later on that in real networks, in real data, that the typical, or the distribution for these little gaps between side branches of the same order, and we won't go into this too much, but it has an exponential decay. It's a nice little exponential distribution. So it turns out you have to somehow sum different kinds of exponentials together to get power law size distributions, which is a fun activity. Somewhat insane. Okay, but we won't quite do all that, all right? Just to tell you. Okay, so this is reasonable for these two really big iconic kinds of branching networks that we have reasonable data for. We actually have, I was talking about Mars, right? Looking at the structure on Mars. So we actually have much better data for Mars's landscape than for the Earth. We sent up there's not much stuff in the road, right? No trees, none of those things. We just ran some satellites around it, and we have really good resolution, which is pretty silly, obviously. So we can really study that one if you want. All right. I think not as interesting, actually. I think the whole rover thing, this is obviously, I know the guy who's from years ago at MIT, Ratzinger. He's been the head. He's over at Caltech now, I think. And so he's the head of the geo part, right, for the rover. So he says things. He's a great guy. I went on a few field trips to the Mojave Desert and Panamint Valley years ago with him and his crew. But so this rover really should be reporting things like it's just as boring as you can imagine, right? Everyone gets excited about like a little donut rock, but it's a lot of red. It's like a lot of red. They should have some comparison rovers, right? Like any good scientist, you should just have ones in Paris. Another one could explore the Antarctic, but the Paris one would be like tasting eclairs and so on, and the Mars one would just like go off into a crater and give up. But anyway, I know it's fun. It's fun to explore the universe where there is nothing, and we're sort of getting the reinforced story that we're completely alone and there's no meaning in life. All right, okay. I think it's a good possibility. Okay, all right. So we're going to talk about. So we're going to say, we'll talk about this thing, drainage density. The DD is for drainage density. It's the inverse of this typical distance between channels, right? Bit of a funny thing, but it's a 1/length scale. But we'll use it in that way a few times. So we have all this data now, right? So you could, or we have this kind of taxonomy of branching network pieces. So we could break it down like this. So if we sum up all of these stream lengths, which is simply to say we actually just sum up stream segment lengths, I should say. That means we just sum up all of these path lengths. We're not double counting or anything. We're just simply, right? If we had to row our canoe up in here, we just take all the pieces that we've gone on only one time. And we divide that by the basin area. Then we've got some sort of typical length scale, which is sort of on the order of the separation of these basins, right? So this is area divided by, length divided by area. This gives us 1/length. And in what we've done so far, this is the way we've set things up. So this is the area of the overall guy. Capital omega is the overall one, whatever that order is. And then the way this, we'll see a few of these things, the way this will work, right? So it's the typical stream segment length of an order omega one, the total number of those guys. So we're adding, so we're counting, lots of counting and adding. And we're summing over all the orders in the basin. Super duper.
How would the basin area be calculated?
You mean, okay, so if you have gridded data, then you're simply,
How many boxes?
yeah, how many boxes? Yeah. So it's a little fractally around here, but this is once your basins get big enough, it's all good. That's a pretty good measure. You can imagine resolution does affect this length thing because of this whole fractal business, but not hugely. Yeah, cool. Coastlines are a little more famously, right? Yeah, okay. Okay, so, all right, we're going to start with Tokunaga's law. Right. Yep, that's what we're going to do. And we're trying to see if we can get to one of these guys. Let's see if we can get to this Horton's law for numbers. So it sort of seems like we should be able to do, right? There's counting in the Tokunaga thing. It's telling you how many side streams are coming in, and somehow we have to turn that into total number for an order and then total number for the next order. Okay. I know, as I've said, Tokunaga very clearly tells you it's not a pure hierarchical structure, and Horton's laws sort of make you think it is. So and people get into trouble when they. So, for instance, if you want to think about the resistance of the blood network, right? So that's a big deal, right? So, if you think of it as purely branching, that gives you a very different kind of, right? You're pushing stuff into this tube. You got your ticker here, right? And it's pushing stuff in. That's a much easier problem to deal with than one that has all this kind of little side branching. Because in fact, you can kind of just add all this stuff up if you like electrical engineering at all. You shouldn't. But then this stuff is all in parallel, and then this kind of the whole thing is in series. Yeah. And for it to be efficient, in fact, what it tries to, what you can argue is that essentially all of these little guys add up so that they kind of look like the same tube as the aorta in a way, roughly. Right? So it's not getting wider or thinner. All of these guys combine, so effectively they kind of have that feel. What's that? Yeah, okay. It's just that they resemble, because impedance is all about what does it look like from the outside. You don't know. So as long as it looks like, yeah. So these guys, from this point of view, you don't know what the details are. You feel it coming back, but if it can look the same all along, that's going to minimize your impedance, which is a good thing, trying to keep existing. Evolution optimizes a few things, but not, it's complicated. Right? Our brains use too much energy, and we watch television with it and so on, so, it's pretty sad, really. Okay, so, okay, all right. Yeah, one of our students is now working, I'm giving you asides because I can't help it, is working on activity levels, right? And so this has been done. So people have measured how much energy you use in all sorts of contexts. So one of them is lying down watching television. Like sitting at a desk with your hands on your head, like that, and it's got its own little, that's different to sitting. But sleeping is just a little bit less energy than watching television while lying down. Anyway, so it's bad to see it in numbers. Makes sense. All right, sorry. All right, so we're going to try to get to this number story. Yeah, it's obviously, math. All right, so, okay, so let's see if we can do this. It's a little, wow, what is this thing? There's a little bit of backwardsness to the way we'll go. Right, but if you have a nice big order omega prime guy here, then that starts to tell you, then you know from Tokunaga, how many of the order, say, omega prime minus 1, and omega prime minus 2, and there'll be some order 1 guys coming in here. You have an idea of how to count up these. So you can start to, you can start to build a story here. So you also know that this was generated, this idea of generated, that this is the way the stream ordering works, is it started with an omega minus 1 and an omega minus 1 running into each other. So you have 2 of these guys, and then you have all of these side branches. Okay. So there are two ways for a stream to not, to run out of being a stream segment. So this guy stops being, let's say, I've got the picture there, so I don't know why I'm drawing it here, but it's going to run into something here. This is either omega prime, this is greater than or greater than omega prime. And it could be it ran into the same order and then it switched, or an order that absorbed it. So there's this case. So here's an order 3 terminates because it runs into another order 3, just the definition. Or it runs into one of a higher order, right? So this could be 4, 5, 6, 7, 8. Doesn't matter. Okay, it runs into that. So this is one way to count things. So there will be, so for every stream of order, so in this case 4, but if every stream of order omega plus 1 has 2 that generated it, right? So there'll be 2 n omega plus 1 of these guys. Yeah? And then we count the numbers that are side streams here. Okay, so what are the things that are terminating these streams essentially? So there's only there'll be one of them. Instead here you have 2, so you have to double count it. One of these guys is running into a high order one. And so the first part is the number of streams of that higher order. And for each one of them, it has this ratio, right? It has a ratio that shows you how many are terminated. And it's that difference, right? It's the difference between the stream that's being absorbed and the stream that's absorbing it. Exciting? Very exciting. It's kind of surprising how this, I mean, it's not like we get a like a 10th order polynomial, but we get something a little not obvious, right? Okay, how do we believe this set of lies? Well, okay, good. Oh, okay. So we are assuming, streams of the same. Yeah, they're only forks, right? They're only yep. So that's a good point. You can only have this kind of structure. It's just junctions of 2 streams. So you have the 3 river. That story, but that's sort of because they changed names, right? That's pretty rare. Well, this title, that's not what you mean.
No, that's not what I mean, but I forget the exact example, but it's basically like
pollution or something?
I'll find it after class.
Or something, okay, something, canals or something.
Weird stuff.
Well, we do mess with these things now and then, it's true. Putting in large dams and so on. Okay, so does this make sense? Let's see. We're going to count them again. There are 2 ways for these things, and they're different in terms of the Tokunaga stories. Tokunaga doesn't count these bits, it only counts the side streams. So when we have a side stream type situation, then for every order that's greater, so in this case it's 4, but for every order greater than the one we're interested in, right, we have so many of them in the whole network, and each one of them absorbs typically this many, which is some fraction, right? So roughly this is the number of order omega streams that are absorbed by order omega prime ones. And then we have these ones that run into the same order. Okay, so we've got those 2 pieces. So we're going to have this plus this. All right, this plus this. Okay. And we have to sum over these things. So, all right, so there's the generation part. Yeah. Right, every stream of 1 index higher was created by 2 of these guys. And then we have this piece here where we start with the stream that's one order higher. We go up to the highest order in the whole thing. There's some small details about finite sizes and so on, but it's okay. And this is the piece we just showed, but we have to sum all of these, right? Okay, so we have these 2 kind of different pieces. This little guy hanging out here, and then this bit. Okay, so now you have Tokunaga's law, right? So we assume Tokunaga's law. So this is true. It's built out of Tokunaga's law. It's starting to get and you can see we have n omegas and n omega plus 1s, but then we have these guys going all the way up to capital omega. So we have a bunch of these guys, and we really just want n omega and n omega plus 1. We want to get the ratio of those two. So this is a fun thing for you to do. Okay, so but you take Tokunaga's law, which again is it's written as a general. It's TK, right? It's T1, just this thing. You can stick that guy in there. So that's just geometric things, and then you get this horrible little beast popping out. But it's it's a solution to a quadratic, right? You want the larger value. We can think about why that would be so. But and there are some smaller arguments in there that can get that. But yeah, so the Tokunaga ratios or constants appear in this funny way. So there are a couple of exact toy kind of values, I think. So for instance, 2 and 1, right? So you get a 5 here. You get 5 squared minus 16. One of those nice Pythagoras things. 25 minus 16, 9. So you get a 3. So this would be 5 plus minus 3. So the 5 plus 3 gives you 8 over 2 is 4. So that gives you a branching ratio of 4. So they're actually kind of on the order of, they're reasonable numbers, actually, which is kind of fun. But, it doesn't, real networks have all sorts of things. Okay, so there's a little thing to work on. But the setup, right? So there's a lot of this. There's an architecture here, and we're just kind of going with it. As I said, we can get more and more insane about the real details, right? This is the average number of side branches, for example, and this is the average area, and you can start to look at distributions. We will do that a little bit, but we don't want to hurt ourselves too much. This is what we do when it goes wrong. Okay. And we need to get to supply networks and all sorts of other good things. Okay, so and I think one thing to think about with all this stuff is embedded in 2 dimensions, and 3 dimensions. We don't have to worry about higher stuff. When we get to random networks, when we get to informational networks, they're potentially much higher dimensional things. This forces certain behaviors. Okay, so that's one. So we've got one of them. So we've got Rn in terms of the Tokunaga ratios, right? Yeah, it's good. So we can connect it to, we can start with Tokunaga, and we can make an argument to get to this is some interesting things. So to get to the Horton ratio for stream segment length, and we know that those two are connected, those length ones are connected. So first of all, we do this. We assume that there's a typical separation of streams, right, as you go along here. This is a bit sneaky. So yeah, so for because Tokunaga is all about counting, we need to get to length. Okay, so if you count up the number of side streams, expected number of side streams, so you go from 1 to omega minus 1, so you're on an order omega stream, so you can have side branches of order 1 less all the way down to 1, which corresponds to T1 going up to T omega minus 1. So you add up all of those guys. You add one more because what you're really doing is saying, all right, and we're going to go from here to here. I'm going to count up how many side streams, regardless of their order. Just going to count all of those. And that will give me all of these little, that will correspond to all of these little pieces. And then there's a +1 for that last one, just to be ridiculous. Okay. Okay, so it's counting, right? It's just a counting thing. So that's the number, and then we have their typical scale. So that's this little guy sitting out the front. And we use drainage density just to be nice to geomorphologists and so on. All right. Again, you can do, now we're starting with Tokunaga's law being true, so we're going to stick this guy into here. So that's just taken, right? We're just going to put this in here. So there's a T1 will pop out the front. That's just a constant. This RT to the K minus 1 is here. This thing? Delicious? No? What's that? Can you remember? I mean, it's not a horrible thing, but what is it exactly? Let's get it. So it starts at K equals 1. It is a, what sort of beast? It is a Chicken. Mm-hmm. Mm-hmm. There's a thing we say about this. It is,
It's a power series.
yeah, but we're doing this thing. It is you've been doing too much of that math. That's what's happened. It's a sum, and it is well, yeah, but there's another word for it. Geometric, like think of, I don't know, 18th century English people saying, right. But it is exponential. It's growing exponentially, you're right. But it's geometric. This explodes into flames, actually. This number is typically greater. This is greater than 1, but it's finite. Right? What's the sum of A? So this is the thing. It's actually just a ratio. It starts, this is really right. It's 1 plus RT plus right? And it actually goes up to, so it's a k minus 1, right? So it goes up to omega minus 2. The question with this is always, what's the power on the top, right? You're always like, is it plus 1? Okay. So the sum of A r to the k equals 0, let's say, to m minus 1. What's that? Does anyone know that formula? Should we derive it? It's a ratio of something. There's an A. The A is there for the whole thing. This sort of thing, have we seen this? And there's a power. This one, it's up to, so k is the index. This is this one? This guy? You're looking at, this is the A here. That's just a little constant. Maybe my notation is funny. Sorry for the suffering. So in this case, we have A equals 1, but we're starting at k equals 1. We're going to omega minus 1, so we have to think about that a little bit. The highest power is going to be omega minus 2 here. So this will be RT omega minus 1 over RT minus 1. Maybe? Various ways to prove that, of course. But okay, so that's the story. This is a constant. This is a thing that's growing exponentially. It's getting bigger and bigger, minus a 1. 1 is just 1. But let's say this is 2. It's 2 to the 7. That's big. 2 to the 6, to the 5. So this starts to be unimportant. So this whole thing is tending towards something that's proportional to r to the t omega, right? Right, for large. Okay? Horrible physics thing. Okay? Occurs. Okay? So that's this little piece on the end. Oh, yeah? This will be important to do these kinds of sums. Yeah, what's it?
Why is it omega and not omega?
It's proportional. Just saying it's proportional to. You can always put a couple up or down. Then it matches this omega, and that's tidy. Yeah, okay, don't.
See what Richard Foot thinks about
Yeah, right. I mean, x to the 11 is proportional to x to the 12 with an x. As long as x is not a variable. Then. Yeah, this is this. So right. So the way to usually handle that sort of thing is to change to another index. And So instead of, this is really going from 0 to omega minus 2. So if we could do this, R2 to K prime. And then we feel better, sort of. Or you could just think you have an A, which is R. Is that what you said? Yeah. Yeah, A is RT, right. They're a lot of fun. And then you get to generating functions. We'll do those things, and then you can do all sorts of crazy things with sums. Because you turn sums into functions. In some weird space, you mess with the functions, and then you come back out and get things for the sums, which is really very nice. And makes combinatorics people very happy. Generating functionology. If you haven't, there's a book by Wilf called Generating Functionology. And it's, you become a black belt in generating functions. It's extremely enjoyable. It's very funnily written. Yeah, kind of a hero. Okay, so definitely a hero. All right. Okay, so if this average stream segment length is growing like this, then the ratio of the two next to each other is just going to be this RT, right? It's growing. I mean, that's what these Horton laws are about, exponential growth, and they're encoded. We've encoded that exponential growth in saying the ratio of any two adjacent ones is some constant. Right? So as we go up, they grow by RT squared cubed to the power. Right. So we've taken this Tokunaga. We found that these two stream segment things can be the stream segment ratio, which we called R sub S, is equal to the Tokunaga rate. So that's nice. Okay, that's good. So the number one is it's a messy looking thing, square roots and so on. But now we have this, right? And we also, you guys will show this for yourselves. We have that the stream segment length ratio and the mainstream length ratio are the same. So we've got this connection. So that's three things. So Horton is here, Tokunaga is here, and then Tokunaga is here and Horton is here. So we have these connections. Very good. Very nice. A little bit of, not evil. It's nothing. It's all very benign things, right? Yeah. Okay, so we can Rn and Rl, and Rs consequent also depend on T1 and R2. You'd think then we'd have to somehow we have to get the area ratio business. We haven't looked at that one, but this drainage density thing should help because we need to. Tokunaga is all about counting, so we should be able to somehow turn that into areas as well, just as we did for lengths. So you'd think we'll get to this guy in a bit. All right, so it seems there's definitely some redundancies, right? We've reduced some things here. We'll actually see this this as well. So this is a nice observation. It was sort of seen at times. This is something we kind of made absolutely clear, so that these two ratios are in fact the same. So we sort of saw that in a couple of those real examples I showed you for Amazon and Nile and so on, that the way the area was growing and the way the number was decreasing kind of looked the same, actually. And they looked, even when they deviate from scaling, they match up. All right, now I've threatened this whole thing about moving away from averages to distributions and total mass. That's all there too, and that can all be interconnected. Okay. So this is a simple thing. It's maybe even just a fun little tiny problem, but we have that. They can be inverted. Obviously, the first equation is very easy to invert, okay? But you can undo some of this other stuff as well, and that just that simple quadratic solution, and find T1 in terms of the stuff. I mean, obviously, you should be able to do it anyway, but you can at least write down the expression. So, I mean, that's just algebra, but it starts to make you think that maybe you can go the other way, right? You're excited about that. Yes. Uniform drainage density makes this a possible thing, so that's something to worry about, but it's not going to change enormously. So there was this is this horrible Adobe thing. I just changed this to a PNG. I mean, this is just, but I changed this to this PNG just before. I'll fix it up. It looks bad, but Acrary was just buffing on the C, the B, and the A. That was it. That was just, and maybe this as well. As far as I can tell. Oh my God, unbelievable. It was one of those errors that you look it up and no one really says much about it. Like why doesn't anyone know? I remember the first time I sort of got to Google thinking, oh, I should just take the whole error statement and put it into Google. I don't know, you know, I mean, obviously, right? But just one day I just thought, oh, I'll do that. I was like, oh, magic, you know, solutions. But so usually you think you're good, but and now it gives you things from like 2003, and you're like, right? What are you doing? All right. Okay, so we're going to see if we can get from Horton to Tokunaga. So we're going to get from this more gross picture, which doesn't have architecture in it, and kind of work our way back. This is all right. So this is a this is a nice thing to do. So we assume Horton's laws, and we have number and length. And let's think about this picture. We have to think about this a little bit, unfortunately. Okay, so this is going to be this little guy in here is an order omega stream in here, and these is an order omega -1. They're a bit hard to tell, but these ones they're the generating ones, and these are the two side branching ones. And then we'll scale it up according to this Horton ratio for length. Right? So Horton ratio for length. So now this guy is of the typical size of the next order up, and so are these, and so are these, and so are these, and so are these. And then to make this thing look it's an appeal to self-similarity, right? So to make this thing self-similar, then we're going to have to add, and to have the right drainage density, we're going to have to add in the next order down. We're going to have to sort of fill these guys in, because now it's too sparse. Okay. Yeah. All right. And we're going to so that's what this last statement is. We're going to maintain the drainage density by adding these pieces in. Right. And then this is just order omega -1 and omega +1. There'll be all this finer and finer detail in there. Let's see if this thing works. Right. So you scale up. So it's a similar picture here. So you scale up this. So here's an order omega -1, say, if I get that right. I think these are omegas to match up with the lies I've told you here. And this is going to be an omega, and it ends here. And it's got all these little side streams, different orders. When you scale it up, you're going to have to add in all these little extra guys to get the right drainage density still. Right? So you're going to reinforce it. So you've expanded the whole thing, and then we're going to add these pieces in. That's not... Yeah, right, sorry. Lies. Organic, locally sourced lies. That's what we do here. Handcrafted, right. Yeah. So okay, so good. So we need to, so we've expanded this by a factor of R sub L, right? That's this growth to get it out here. That was the picture before. So now we've got all of these little extra guys in here that we have to add. So in here there are now RL -1 first order streams. So we're going to add these guys. Kind of madness. Right, before it was this kind of picture like this. It was, it was a smaller scale, and we've expanded it out. So for the whole thing to have this self-similar feel, should do this. Okay, so RL -1. So there are those many because of that +1, right? So RL -1, you add up all the little pieces, and there's one more on the end. So that gives you RL, like we had for that previously. This might be a bug in the slide. I think I fixed it. So this omega +1 stream will have, it has to, this is just by definition, and it's a self-similarity argument. The number of first order side streams in here has to be T omega. Right? T omega equals the total number of, or the average number of first order streams, first order side streams. there's a, we can say in general we can connect it. Well, we have to count up how many side streams there were before, or how many of these little gaps there were, right? So it's that same thing we did before. It's add up the total number of side streams of all kinds, and so we go from I equals 1. I've changed, I guess it's going to k. I equals 1 to k minus 1, and you get a plus 1 for this last little space here. And then they're all ramified, right? They're all given these extra streams. So that's this extra growth factor of RL minus 1. A little bit of funny business, but you can kind of argue this way. So it's a pill to self-similarity. It's not at all obvious that Horton's laws imply this kind of side branching structure at all, but one can kind of get your way there. I mean, it's the funny thing. So the algebra, well, you know, the going from Tokunaga to Horton, which you feel sort of brave about, like you feel like you can do it, and you accomplish that. And then you notice that there's not, right, that they kind of match up in number of terms, that you might be able to go backwards. So we can check, so we're going to check to see if, so you can figure this out in different ways, but let's at least here just put in Tokunaga's law and see that it works. So this is just a little bit of tribulations here. So this is exactly the same statement. And we're going to stick in Tokunaga's law. There's T sub I, so we'll write it in that form. Yep, and we're going to change. We know at this point, right, that the ratio is Tokunaga's ratio is the same as, the Horton ratio for length. All right, super duper. Okay. All right, so we stick this in. So we're going to take this business here. We're going to stick it right in here. Look at this, right? It looks like something bad happened. I think this sum should be here. Yeah. Okay, that's bad.
Should be 1 plus the sum.
Yeah, 1 plus the sum. That's funny. Bugs. All right, so this should be, it should be out there. This sum is here. I could edit it now. And so, and our RL, this is really just replacing it. And then we do one of these geometric sums again, okay? So there's a T1, that's just a constant. We're summing from 1 to k minus 1. So one way to think about it is our A, right? Our first one, we're not starting at I equals 0. We're really starting at, we're starting at I equals 1. One way to make it start at 0 is to just pull off, or is to think that the one of these guys is A, right? You could do that. We don't want to do that. That's a bad. No, we're not going to do that. Okay, so you just move the index down, right? So we're going from, yeah, that's not right. We're moving the index down. So we're going to go from 0 to k minus 2, and this index up, this power will be I minus 2. Or just I. It'll be I. And if you do that, you're going to have RL minus 1, right? That's our ratio here. That's going to be RL minus 1 here. And it's the power here plus 1. So it was going to be k minus 2 plus 1, so it's k minus 1. Geometric sums, right? Okay. So there's a few of those guys floating around. So again, this is, you know, some constant. This is a constant. This thing is much larger typically than this. So that's the next step here. This is much larger on the top. These RL minus 1s cancel, which is nice. So really the only approximation was here and here, getting rid of those things. Not bad. And so it looks like, so it's a consistency thing, right? So tk equals this, and that should be a k as well. Well, that one had a lot of trouble. Okay, so scribble. Okay, so that's good. So so that's a bit, it's a funnier, not as pleasant kind of, you know, not a simple mechanical argument, but it's not bad. All right, so so that's interesting. So those things kind of fit together. But Tokunaga's law is the more primitive kind of thing. I think in some ways it's the better architectural story. So so here's the Nile and here's the Mississippi. These are plots I've showed you before. So this has number going this way, right? The stream order this way. It's on a log scale. This is 8 orders of magnitude here, 7 here. So this is area growing, length growing, and here we have length, mainstream length and stream segment length. That's those two guys. So we can you can see very clearly the same kind of ratios. So all right, so we're going to flip. That's all that's happening here. We're going to flip this, and it'll be a plot of area and number with number inverted, right? So it's just turned upside down. Yeah, things normalized in certain ways. That doesn't matter too much, right? Just shifting this log scale. So you see, actually, they really match up, obviously, in scaling ratio, but even in detail towards the end, even where. Oh, it fell off. This guy's a little. It's actually just a battery. Hold on. Thank you. I need a Bungard kind of robot that runs around, ridicules me or something, taunts me. Yeah. Okay. Thank you. Good. Okay. So yeah. Right. So we've flipped the stream up. So this is suggesting there's some connection. Yeah, a little bit. So let's figure that one out. And that's something actually you can solve. So we'll get to that. All right. That means though as well, we've only got two parameters for Horton now, which matches up with the two parameters for Tokunaga. Okay, so that's good. All right, good. This is sort of a problem associated with this, with power laws and all sorts of things. This, we are talking about exponentials, but in a way, the orders themselves are exponentially kind of growing things. So the fact that lengths and areas and numbers are changing exponentially, we'll see are connected to power laws. This gives you an idea then, so we're going to just regress on these things. This is just sort of a side piece. So you just do a linear regression, right? We've talked about it a lot in POCs. Yeah, too much. But you get these different estimates. So it's, right, so if you just do regression ridiculously on just, 2 points, right? But these are, you don't have many ranges. So 4 to 8, 4 to 6, this is just sort of sweeping across different things. And then, just for fun, you take the mean of all these, the standard deviation and so on. These guys are typically pretty consistent with each other, and so are these. This is the ratio of area over number. This is a look at how really correct this ratio of area to number is. This seems like, if anything, there's a little bit of a skew one way. That area is the area ratio is a little bit greater than the number ratio. Right? Depends how you measure these horrible things. Yeah. That's Mississippi. Amazon, sort of a similar result. So again, the stream length and stream segment ratio is pretty similar. These guys are, again, pretty similar, but the area one's always just a little bit bigger. But, at least analytically, not so bad. So let's do it roughly using this kind of hierarchical view, but if you need to really use the Tokunaga picture properly, which it's good. You have to really think about these architectures. All right. Okay, so the area of a basin is going to be the sum of all these stream segment lengths, what we talked about before when we did drainage density, right? So we're going to sum up all these stream segment lengths. So here's this bit, okay? And then, yeah, it's a bit funny what we've done. But there's a typical scale in here. The inverse of that will give us an area, right? So we've got all these things, and we multiplied to get this typical scale in between them, and it expands it out into an area. So this is a rough estimate of the area. So let's do some things with this, right? So it's just sums. This is nothing super out of control, but you know the way you treat sums and so on. There's some nice sneakiness in all of this, right? So let's see. So number is something that is decreasing. Stream segment length is is increasing. So let's expose those pieces. So we've got our sum still. A nice way to do this, well, we know exactly how many there are of the highest order, right? There's one of them, so it's good to peg that guy. Like we don't know how many there are of the little guys. That sort of depends on our resolution and how big the basin is, and, right? So let's start with that one and then go backwards. So to get n omega, we're going to peg it to how many there are of the highest order in the basin, and then grow back the other way, right? So n omega, let's see. So n omega equals 1, n omega minus 1 equals Rn, and then n omega minus 2 equals Rn squared, right? And so in general, and this is a K. Oh, little omega. All right, this guy, right? That thing I was talking about the other day, you want to make sure that, so, right, this plus this plus this plus this, they always have to equal capital omega. Just, you know, mindlessness. Okay, so that's kind of good, all right? And then we have a typical size of the smallest streams. That's something about the landscape. So we can start with them. So we start at the other end with those, and we're going to grow out from there. So when omega is equal to 1, then this is just S1. Omega equals 2, then we're at, you know, we've grown up by 1 ratio RS. So this is all right, just, okay. Is that okay? I know, it's math. But it's thinking about the physical system and what we can actually define. We're good with 1. 1 is an excellent number, okay? And this is something that's got something to do with the landscape, yeah. So then we can go to bigger and bigger basins. All right, so this guy can pop out. These are fixed, right? This capital omega is here, and this, right? So this guy is going to sneak out. That's just a constant function of the basin. There's an RS and minus 1, so that's going to pop out here. And then we have this nice looking thing here. That's a ratio of these two guys, and this is, again, a geometric sum. This ratio is now smaller than 1, so it will converge. So we can treat that a bit differently. Super exciting. Yeah. It's good. All right, so this is our story. We have some junk out the front. We have to think about that big omega. We don't want to throw that away. Yeah. That's what I did. Yeah, all right. Yeah, that's right. That's right. Okay, that's good. Okay, yeah, all right. So I pulled one of these guys out, fine, and then it's really the sum from 0 to omega minus 1. Sorry. Yeah. So this is a geometric sum story again. So this bit is going to decay. This is smaller than 1, so this thing's going to disappear. So we can neglect this. So that's what's happened there. Some of these things can be just, right, we'll multiply through and some other pieces disappear, right? These guys cancel. This guy cancels here. We've still got this. And so this, right, constant, this is the big piece here. Okay, so I know this was just algebra, but what we were looking for is how does the area of a basin of size omega scale or behave as a function of these Horton ratios? And so we've got this out. It's growing like the number ratio. So that was kind of nice. All right. So this is the thing that's observed, and yeah, good. So it's growing exponentially, and that, you know, that's our ratio story. All right, so we've collapsed a whole bunch of this description. You have to be, this is a rough argument, actually. So you need to actually think about side branching, which is a nice problem. It's a nice problem. It's a very nice problem, and you get to do it. Okay? Yeah, because what happens is, you know, if you're at the scale of a basin within a much bigger landscape, then there's some sort of funniness for just that first order down. Once you get into the very small basins here, there's lots of averaging and lots of goodness in there, so you can kind of treat them in an okay way. But the fact that you're in a much larger context means there's something a little bit special about your basin that Tokunaga's gives you, but it's not exactly what you. Right, so that's a fun thing. So this is kind of a nice result. yeah, sometimes I thought it was sort of a publishable thing. I don't know. You see this in some other kinds of systems. If the number and the area, right, are growing in this kind of inverse way, right, then you multiply them together, so you get the total area for small guys and the total area for larger guys and the total, right? So the total area for order omega equals 3, 4, 5. They're about the same, right? Because they're balancing each other. It's not really, I don't think that's obvious. And it's not obvious even after thinking about it for a while, when you cheat and say it's obvious, right? It's not that obvious either, the different levels of obvious. Obvious is just a disastrous word. It's just, you shouldn't use it at all. Okay. But it isn't really clear at all that this would be true, right? There's some ideas that maybe this is the case for organisms, right? So the energy that organisms use increases, of course, with size, but so does their, but at the same time, so the range also increases, but and their population density decreases, right? There are less elephants than there are squirrels, right? And then there's this sort of suggestion that kind of they balance, right? So that the total consumption by elephants is about the same as squirrels. I don't know. I mean, it just sounds nice, and it makes you, some people sort of start talking about religious things, but it's, it could just be that it could be that systems have to be like that, or there's an instability, like they start to blow up or something. I don't know. But this is right. So this is this observation, which comes very clearly out of these laws, is that this is roughly a constant, and I've just talked about this. And so here are a couple of examples. So it blows apart at the ends when the orders are high, and they're much fewer, of course, and then the large scale structure matters, right? The mountains were here because of tectonic plates and things. So the Nile, for example, is quite long relatively, and so on. So that's going to sort of fall apart. It has to be that at the way this is, okay. This the scale here, this is the total area of basins of order omega, right? So you look at all of them. This is why this is so weird. So here's an area 3 guy, here's a order 3 guy, order 3. They're all disjoint, right? They can't overlap each other. And then there are order 3 ones out here and order 3 ones. If you add all of them up, and then you go to order 4, and so order 4s will be like this, and there'll be an order 4, it's not quite true, but there'll be order 4 around that one, and so on. And you add all those up, they somehow kind of patchwork together to give you a similar kind of thing. When you go to the whole basin, its area has to be the total area, right? So its fraction of the area has to be the total. So that's why, it goes to 1. But roughly as you go across, there's sort of this, and this is true in these very different continents, 60% roughly, kind of. This is some architectural thing that is beyond stream ordering, actually. But why don't I publish this? Okay, so I honestly have a paper on this, which I've probably written 3 times. Okay, yeah. So it's kind of nice. I think it's nice. It's a nice thing. Okay. All right. So we have this. We have these natural branching networks, which are everywhere. I keep harping on about these 2 particular ones, but for these I have data to show you, and you can think of other possible examples. Body ones are a bit funny, right? There are different kinds. The ones in the liver are different to the ones in the kidney and so on, and there's the overall blood ones. The brain ones are obviously very different as well. So we have a whole collection of interesting kinds of networks that we are walking around with every day. It's a mixed kind of hierarchy. There's all this beautiful self-similarity, but it's not. Hierarchy is a bit of a dangerous word because we tend to think of it as but it's mixed. And Tokunaga's law we see is really, that really clears things up. As I showed you, hard papers to, even though I do supply you with the original material, it is hard to immediately fathom unless you, of course, can read Japanese, the original work. But we've got the idea, so it's out of that work, and it's great. And so we also see there's only 2 of these laws are independent. There's the stream ones, the length ones, and then the number and area ones are the same. And then we have this nice connection between these two parameters. So that was good. That was a nice afternoon's work, right? Chiseled it down. Okay. Okay, so I'll just start this a little bit, and I think I do want to try to get through this on Tuesday, so I think that would be good. But you know, as you'll see as we go on, there's just all this richness keeps kind of coming out. But I think you can see there's a lot of structure already, so that's good. All right, so let's go back to this idea of, and I mentioned it earlier when I showed you all those different laws and kind of relationships. We pick a random point P on the network, and there's some basin associated with this guy and some stream length. And then what's the probability that that basin has area A, and what's the probability that it has a mainstream length of length L? So we get power laws because we live in the universe, right? And statistics of surprise are good. So A to the minus tau and L to the minus gamma, right? So these things are all over the place. And well, you guys, if you've done POX, if you've gone through the fun that is POX, you will understand these exponents. So tau is typically between 1.3 and 1.5, and there are very nice little toy models for which there are specific kind of values. So that's pretty extreme, actually, right? That's an infinite mean situation, which is nasty. And gamma is between 1.7 and 2.0. So there's a random walk model. You know all about random walks, right? So we talked about random walks in POX. If we didn't, it's okay. There's a first return kind of thing that actually works for as a toy model. And you remember that first return exponent? Remember the exponent for that? So this is the person who is incapacitated for some reason. They have eaten something or consumed something that has made them move randomly. And they have left where they started. And then what's the probability that they come back after t lurches backwards and forwards? Right, and that decay is t to the minus gamma. It's normalizable. They will always come back. If it was in 2 dimensions, they'd always come back. If it was 3 dimensions, they won't. And this is very famous mathematical work by Polya. So it's the recurrence, or what's the chance of escape for our random drunk friend? Incapacitated. Yeah, flying is really bad. Yeah, if they lose the ability to be held down by gravity and just sort of start lurching like that. Yeah, they have a chance of never coming back. In space, I guess. Yeah, they leave the space station. And, I guess no alcohol in the space station for this very reason. I'm just kidding. I'm sure there are other reasons. Sorry. Oh dear. I'm just. Yeah. Okay. Yeah. I guess you could. Yeah. Right. And they're very smart people, right? So yeah. It probably gets pretty boring. So I guess. Okay. These are infinite mean situations, right? So your friend comes back, but it takes an infinite amount of time on average, which is pretty bad. Between 2 and 3 is infinite variance and higher moments, but finite mean, which is an interesting kind of distribution. We see those things a lot too. So, right, lots of them are like that. Above 3, we're like, it's not even. You can keep it. Okay, and just to reprise, we've seen these things everywhere. Complex systems thing, right? We have the mechanisms, blah, 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 right? So here again, I mean, there are very real physical mechanisms producing these things, producing us. We're always trying to get to these guys, but it's hard. Yeah, see, not a real mechanism. That's right? Okay, good. Good example of not a real mechanism. Okay, and I'll tell you where we're going to go next. We're going to derive these guys. We'll connect those, because these are big stories. And we're going to do this, bite, stick, proceed. So we'll figure out how to do that. We'll get that from Horton's laws or from Tokunaga's laws. You should be able to do either, but now we've bridged those, it's okay. So, okay, thank you. So I think I'm going to make the assignments not every week, but if they per request, so that you might get 2 assignments at once, so you can pretend they're one assignment. rather than me
but they're small.
merging them.